All right. We'll start now chapter 11. And as always, the comments are on. If you want to correct something, mention the minute and the second and correct it. If you want to elaborate, if you want to add something, feel free to do so in the comment section. Also, all credits for the slides goes to the KFUPM University, so the slides won't be shared. Data link layer. Functions of the data link layer include data link control DLC. It deals with the design and the procedure for node-to-node communication, and the MAC, which is the media access control, which deals with the how to share the link. And as previous, we saw that broadcast link contain both sublayers, the DLC and the MAC, but when it comes to the point-to-point, we only care about the DLC. All right. Data link control function include framing, flow, and error control protocols implemented to provide smooth and reliable transmission of the frames between nodes. So the framing, the first job that data link control do, which is framing, it links the data link layer packet bits into frames, add sender and destination addresses, as we saw previously, to each frame, so that each frame is distinguishable from another. We have two types of frame, fixed frame and variable size frame. So we have fixed size frame and variable size frames. So with the fixed size frame, no need to identify boundaries because it's fixed. So the starting and ending points are always constant and known. The size is the size itself can be used to identify the starting and the ending point. An example of this is the ATM1, which uses frames for the fixed size called cells. But the variable size framing that we are going to focus on this chapter, as the name implies, it's variable. So maybe sometimes it's 10, sometimes it's 8. The sizes change. So we need something to identify the starting and the end point for each frame. So we have two types of this: character-oriented approach and bit-oriented approach. Character oriented approach, it's an 8-bit character carried an 8-bit characters from codec systems such as ASCII. So you have the flag at the end and the start of the frame. We will have a header, a trail, and the data itself. So here it's just telling you the flag, it's 8-bit in size. It's telling you the beginning and an end of the frame. And also separated from the next, and of course the flag separated from the previous and next frames. Okay. The header also, it's 8-bit, and it's contained the source and destination addresses, as we know. The trail used for the detection for error control. Okay, and it's also 8 bits. It's used for error detection and correction redundancy. So trail used for in the error detection. The header contains the source and destination address. The flag, we use it to distinguish the starting and the end point of the frame, and so that we can distinguish that this frame is different than the previous frame that we have and the next frame that we have. We have the concept of character stiffing and character unstiffing. Simply, whenever you receive a data from upper layer, it will contain a flags, it will contain ESC character. So the concept is simple. Whenever he asks you to stiff the given data, before each flag and each ESC, you will add an ESC. So we will add ESC here, and we will add ESC here, as you can see, before each ESC and flag. Okay. Escape, I guess it's abbreviation for escape. So before each flag and escape, we will add an escape character. Okay. The special character is added. Okay. So simply, whenever he asks you to stuff a data from an upper layer, go to each flag that it's contained in the frame and each escape character, and put before each one of them an escape character, as he did here. So now, unstiffing, we will remove the flag and the header and the trial and the flag, okay, because we don't need them. Now we are doing and decapsulating, and also we will do the unstiffing processing. So we will remove the escape character that come before each escape character from the data, and the flag also. We will get the original data now, okay. So the stiffing, simply adding escape character before each flag and each escape character, like this, like we did here and here, and unstiffing, just removing the escape character from each uh, from each just removing the escape character that comes before each flag and escape character, okay. Here it just do a simple framing, of course, because it's a frame. He will add the flag to distinguish this frame from others, and he will add a header that contains the source and destination address. He will add the trailer that used by the detection error control in order to detect if there is any error or something. Yes, the bit-oriented deals with the zeros and ones, okay? Same concept, but here the flag is a special character. It's not written as flag, it's written as 0, 1, 1, 1, 1, 1, 1, then 0. It's constant. This is abbreviation of it. The 0, then 6 ones, and then 0. And the header and the trial also needed in the bit oriented also. The data will be represented in binary, and we will know now how to add the zeros and ones. So simply, whenever you have five consecutive ones followed by a zero, you will add one extra zero. Okay, so let's see here. He asked you to stiff this data that has been given. So whenever you have a zero followed by five ones, you will add a zero. Okay, so here you have zero, then one, two, three, four, five. You have five ones, then here add zero. Okay, so you got it here. It's zero. Now look for other zero that follows that have five ones after it. Here we have a zero. We have one, two, three, four, five. So we will have also here another zero. This is it. Is there any zero that follows by five ones? No. So this is the stiffing part. Just add zero after each zero that get five ones. Okay. Then the flag, of course, will remain the same. The flag is 0, 1, 1, 1, 1, then 0. The header the same, the trail the same. Then when he asks you to unstiff, you will go for the same process, but now you will remove the 0 and you will get the original data. You remove the 0 by the same concept. You will see where is the 0 that follows by five ones. Then you remove that 0 that comes after it, and so on for the rest of the frame. Okay. Flow and error control. The most important responsibility for the data link layer is the flow and error control. As we studied previously, this is a push type. So the producer, the sender will keep sending it to the receiver. Uh, as long as the receiver does not complain, if he almost get full or he's overwhelmed or etc., he will tell the sender via the flow control to slow down the sending files and so on. So this is a responsibility for the flow control. So the flow control sets the procedure used to restrict the amount of data. So whenever I'm approaching, I'm almost reaching a full or etc., I will tell the sender to slow down and so on. The call is not overwhelm the receiver, so it can limit the speed, or it can limit the amount of memory, a limited amount of memory in which to, okay, the receiver must be able to inform the sender to send fewer frames or stop temporarily. This is and it will tell them by the flow control, okay? The buffer, you can say it's like a temporary memory in the receiver side. Uh, you can say when the buffers begin to fill up, then it will start to tell the sender to slow or stop transmission via the flow control. So the buffer is just a block of memory. All right. Um, Error control. general error to control refers to both error detection and error correction. So it will detect and also correct. It allows the receiver to inform the sender, like there is frames that has been lost, or I didn't receive it, or etc. And it will ask them to retransmission that frames that are being missing. So it will ask only for the retransmission for the data, the frames that have been lost, not every frames. Okay, not all frames, only the frames that have been lost or corrupted. In the data link layer, the term error control refers mainly to methods of error detection and retransmission. This process is called automatic repeat request ARQ. Okay, let's see how data link can combine framing, flow control, error control to achieve the delivery of the data frame one node to another. We have two protocols channel. We have based on channels, noiseless channel, which means it gets no errors. It assumes the perfect environment, that there is no error. The noisy, which is the real case example that there is error. Okay, so in noiseless, we have noiseless error. No frames are lost, duplicate, or corrupted. So we assume the perfect environment, nothing is wrong. Okay. We have two protocols, simple protocol. There is no flow control, just the sender will keep sending. Stop and wait, it will provide flow control because whenever a sender send a frame, he will wait for an acknowledgement from the receiver. Okay. Both of them provide no error control because we assume already that it's noiseless, it's in the perfect environment, so there is no error at all. Okay, so in simple, no flow control and no error control. It will just keep sending to the receiver. Uh, Receiver can never be overwhelmed because with incoming frames, so we just assume the perfect environment. Okay, the sender sends a sequence of frame without even thinking. Okay, so we just keep sending, keep sending. I don't care about anything. Does he receive it? Does he overwhelmed, etc. I don't care, and he won't get any of this because we are in the perfect environment called noiseless channel. This is for the simple protocol. What about, yeah, the flow of the simple protocol? We talked it already, just send, okay? What about the stop and wait protocol? The sender sent one frame, then it waits for an acknowledgement. Uh, so it will send one data to get acknowledgement. It will send another data to get acknowledgement, and so on. So it won't send uh, a frame after a frame after a frame immediately. It will send the frame and then wait for an acknowledgement and so on. And also here is also it's assume no errors and so on. But it got the flow control. Yeah, it got flow control, but no error control because we already assumed that noiseless channel got no errors at all. So it's the perfect environment, imaginary environment. Okay, the noisy, which is the real life example where there is real life errors and so on. We have three protocols: stop and wait ARQ, go back and ARQ, and selective repeat ARQ. Here is telling you that the symbol and stop and wait protocol are still in used, but the go back and selective repeat disappeared. Okay, so we will just maybe take a look at the stop and wait ARQ. Both of these are not used anymore. So stop and wait ARQ, same as the normal stop and wait. Actually, I didn't see any differences, but here it's implies that there is differences. Like there is a timeout timer, and also there's sequence numbers for the acknowledgement and for the packets. I don't see any difference from the normal stop and wait actually, but just try to memorize it, okay? So the side of the send window, as always, it's 1. Thus, the minimum number of sequence numbers are in the stop and wait argue, it's 2, which is 0 and 1, as we will see in the figure. So here it sends the first packet, the receiver receive it, then he acknowledge it. It will move to the next. He sends the other packet, but it's lost. So it didn't receive an acknowledgement. It will resend it after the timeout. It will resend it. Then it will get acknowledgement. It will go to the next one. It will send it. It received it, but the acknowledgement this time is lost. So after the timeout, because he didn't get acknowledgement, he will think that it's corrupted or lost. It will send it again, but it's already there, so it will be discarded, and the same acknowledgement will be sent again to tell the sender to send the next packet. So it's like the normal stop and wait. Okay. Piggybacking, the concept of piggybacking. allow data to flow in both direction, so both data can send acknowledgement and data at the same time. Okay. However, to make communication more efficient, the data in one direction is piggybacking with the acknowledgement in the other direction. When node A is sending data to node B, node A also acknowledge, yeah, the concept of piggybacking. Both of them can send and receive and acknowledge data at the same time. Because piggybacking make communication at the data link layer more complicated, it's not a common practice. So we won't use it in the data link layer, okay? Because it makes things more complicated. That's all for chapter 11.